Yeah, we just started doing interactive systems, right? So we are interested in systems that, oh, not in a parabola, sorry. In some sort of box. And it doesn't have to be box, it could be infinite volume also, no one cares, where we have particles that are actually experiencing each other's presence. Earlier, what we did was we had lots of particles in the system, but we assume they are all either there is no potential at all and everything is perfect and ideal, or we assume there is a potential, but everything is experiencing the same potential and not talking to each other, right? That's how we did quantum harmonic oscillator. And that was quite powerful. We got our heat capacity curves and things like that. If you remember all that, AT cube for phonons and BT for electrons, that was all assuming non-interacting systems. Sometimes it's worked. For electrons in the metal, it kind of works because quantum mechanics is funky. When you look at only s electrons, or some of like electrons in the valence shell, you can kind of approximate that it's like an ideal gas. It works, except when it doesn't. When you go to high level of quantum mechanics, things like iron, the simplest fact of trying to calculate what is the potential between two iron atoms as you pull them apart from each other is actually really, really hard. Methods like density functional theory have a disaster in working on it. It just doesn't work. You have to do very accurate, I think even coupled cluster calculations, which are really, really hard, do not work. You have to do extremely complicated things just to calculate what is the interaction if this was iron and this was iron, and there was nothing else, only two particles. What is the interaction between both of them? That's really hard to calculate, right? So we are not talking about things like iron. We are just talking about simpler things. In fact, what we are going to do next is kind of agnostic to what is U of R. We are not trying to calculate U of R. We are trying to develop a framework that either allows you to calculate thermodynamics from U of R or allows you to measure scattering and come back to something about U of R. That's the framework we are trying to develop for classical fluids. So we are interested in, so actually your answer was correct to a first approximation, but we are interested in classical fluids at low density limit, right? So that's why our partition function, the full partition function, was 1 over n factorial divided by lambda t to the power 3n integral drn e to the power minus beta u of rn, right? And I want to emphasize that this capital U of Rn is the n-body potential, okay? So, and we will be getting into, and my handwriting is going to make you suffer so much, and I'm really sorry for that. Yeah, it's going to be like this disaster. U of R, because I cannot really distinguish my capital U from small u. You will learn. So this capital U is the n-body potential. This is going to be sum of terms that go from I is equal to 1 and depend on some ui, which is now just a function of ri, right? This is what we were doing in the free electron case. Everything is, the potential energy is separable. Then it will have more terms which have I, j, and both of them going up to n. And now you have a potential term ij that depends on both ri, rj, plus you could have three body terms. Like I mentioned last time, right now it's a very hot topic in computational chemistry to use neural networks to fit these things. These are called machine learned interatomic potentials, or MLIP, machine learned interatomic potential. Okay, so and those are really, really powerful, and a lot of people are starting to use it. But of course, like any machine learning framework, there is always a question: does it work outside the training data set? That's up for discussion. So, so for this setup, we are trying to come up with a language to describe the system. What I did last time was really introducing you. I mean, StatMech is already a new language, and within this new language, it's like when you study English formally for the first time, right? You start studying English, then you study prepositions, conjunctions, whatever. So I started introducing the new framework. So let me recap that so we become comfortable with it once again. So let me draw my box again. And today my volunteers are going to be Artley. What's your initial? AD, right? And Rachel. Atley is very happy. Rachel is not happy. She was trying to play tricks on the homework and it did not succeed. Sorry, Rachel. So there is some interaction between them, and there are other particles also existing in this system. And we have some x, y, some coordinate system, right? X, y, we use our cross rule, z goes up. And let's say there is a vector that goes up to particle number 1, which is Atley in this case, and particle number 2. So let's say Atley is particle number 1 and Rachel is particle number 2. Atley's vector is R1, Rachel's vector is R2, right? So the first thing we defined last time was the distribution function. What was distribution function? Distribution function was, there was a hierarchy of distribution functions, right? So distribution function, the first one was P1 of R1. What is the probability of finding particle number 1? In this case, Atley. So distinguishable, right? We are really focusing on one particle, that very particle. What is the probability of finding particle number 1 at vector R1? This will be proportional to integrating out every other particle. If I'm just interested in knowing where is Atley located, and I don't care about what everything else is doing, I need to average out everything else, right? I need to consider all possible ensembles, all possible arrangements of what everyone else might be doing. So I go to dr3, drn, everything, and I integrate out e to the power minus beta u. In this case, this is the n particle many-body term. And I wrote proportional because if I didn't want proportional, I would have to write this 1 by n factorial and thermal wavelength and things like that. Okay, let's call this equation 1. Let's call this equation 2. This was the one particle distribution function. I could describe similarly P1 of R2, P1 of R3, a family of one particle distribution functions. Then I went to two particle distribution functions, which now looked together and at particle 1 and at particle 2. So again, I have given identity. I'm looking at Atley and Rachel at the same time. I cannot mix it with anyone else. It has to be these two, and I cannot even swap both of them. If they swap chairs, it's a different thing. It's a different quantity. This one will be now integrating out dr3 to drn e to the power minus beta u rn. Okay, this is the two particle distribution function. Then we said, well, I'm going to be fair. I'm not going to distinguish between Atley and Rachel. You're all my StatMech children. You're all same to me. Okay. Huh? Hey, it is what it is. Being very fair. So, and in fact, I'm not going to distinguish it between any of you. Biophysics, chemical physics, chemistry, it's all the same. Once in a while, I have mechanical engineering students. One time I had an applied mathematician. His homeworks were funky. The easiest problems, he would have the hardest time. The hardest problems, he would start with like lemmas and corollaries, and it's a lot of fun. So what we did next was to talk about reduced distribution function. We said, what if we are not interested in finding exactly particle 1 at position 1 and exactly particle 2 at position 2, but any particle at 1 and any particle at 2. Okay, so that led us to reduced distribution function. And reduced distribution function is really relevant to our setup for classical indistinguishable particles. That's how we think about a fluid, right? I'm not caring about which water molecule, right? And all they are all the same. So in that case, and I'm just going to write down, I will write both of them. I first introduced rho 1, which is the one particle distribution function. What is the probability of finding any particle at R1? Well, it is going to be n multiplied by the probability of finding one particle at R1, right? Then we introduce rho 2 of R1, R2. Now we have to pick two particles. The first particle can be picked in n ways. The second particle can be picked in n minus 1 ways, right? So this is going to be P2 of R1, comma R2. you could similarly write down the 3-particle reduced distribution function, so on and so forth. We don't really worry about 3-particle stuff. So this we call equation number 4. Then we made 2 claims and proved both of them. Claim 1 was for uniform isotropic fluid, while claim 2 was for uniform, and I want to emphasize this very, very carefully, that there is a difference between both the claims, with no interactions. Claim 2 applies only to a system where there is no interaction between particles. Claim 1 does not apply to this bottle of water, because this is not an isotropic system, right? Gravity is acting. So along Z, this is not isotropic. Along X and Y, it is sort of isotropic, right? But if you took this to a space shuttle, then this becomes isotropic. Even though the molecules are talking to each other, this is still a uniform isotropic fluid. If you took this bottle of water to a space shuttle, claim 2 will not apply because there is interaction between particles, okay? So claim 1 was that for a uniform isotropic fluid, rho 1 of R1 is nothing but the density of that fluid or number by volume, okay? And claim 2 was that for a uniform isotropic fluid with no interactions, rho 2 of R1 comma R2 is equal to rho square. And it looks like, why do I need to make this assumption? It almost looks like the first one, just square it, it should look the same. No, but when we did the proof, we split P2 is equal to P1 multiplied by P1. We assumed independence over there, right? So let's call this equation 5. Let's call this equation 6. And equation 6 is, let's take a moment to stare at it. Equation 6 says, it's quite intuitive if you think about it, right? It's really saying that if you have a uniform isotropic fluid with no interaction between the particles, the probability of finding a particle 1 over here is going to be density. If the density is very low, you will have no probability. If density is very high, you will have some probability. And this probability will not depend on where you're trying to find it, right? Since it does not depend on where you're trying to find it, if you put it another particle and they are not interacting, the probability of finding 2 of them is just going to be rho square. Right? So that's the idea. And I call it, it's not really probability because probability should be normalized. So, you know, it's a distribution function. Okay? It's proportional to probability. So now I introduced something last time, and this is where we are really going to pick up today is, well, what about other things? What about things where there are interactions, which is almost everything else, everything in life? In general, for a non-isotropic fluid with interactions, and what I'm going to write next is very general. It does not even need classical fluids. You could do it for even quantum fluids if you wanted to use it, because it's sort of an inverse definition. I said, well, if you look at this equation, you could write it as an alternate form of this equation would be rho 2 of R1 comma R2 divided by density squared is equal to 1, right? I just took the right-hand side and brought it to the left side. So for an uniform isotropic fluid with no interactions, this thing is equal to 1. For anything else, what will it be? Well, we don't know. It might be 1, it might not be 1. It won't be, it will probably be a real number. I don't think it's going to be a complex number that we can say. It'll probably be a positive number. You know, it's some sort of probabilities, but it could be any positive number, right? So what we do is to call that thing, which we know is something. It sounds very philosophical, but that's what it is. We don't know what it is. We know it's something. G2 of R1, R2. Okay. And this G2 is the third thing we introduced last time. This is called the decorrelation function. And it's really a vector. So if G2 is equal to 1, you have an independent system. there is no interaction, right? So G2 quantifies non-independence. And you could use this type of setup. People use it for Noah loves astrophysics. You could use this to describe white dwarfs and black holes or whatever you're interested, right? There is nothing classical needed. It's just a setup for describing things, right? So people like Subramaniam Chandrasekhar, who doesn't even know who is Subramaniam Chandrasekhar apart from Noah? Or even Noah? Do you know who he is?
Yeah.
What did he do?
He determined the maximum mass for white dwarfs.
White dwarfs. Then what happens after that mass?
Then you have a type 1a supernova, which has a very specific and well-defined
things go crazy beyond that mass. That's what he's trying to say.
And the brightness of those is very consistent, so you can actually use it as a standard candle to gauge how far away a galaxy is.
So if you want to learn about that, you can ask him. So I also mentioned Subramanian Chandrasekhar. He's very interesting. So he won the Nobel Prize. He did the work in 40s. He got the Nobel Prize in 80s or something like that. He was at the University of Chicago because there was this guy, Eddington, who did not like what he did. And Eddington had to die for him to win the Nobel Prize. His uncle was also very famous. His uncle was Raman. And if you have done Raman spectroscopy, you know who that is. His uncle also got the Nobel Prize well before him. So from India, there are only two people have won physics Nobel Prize, and they were uncle and nephew. That's insane. So, okay. So if you read the YFH Subramanian Chandrasekhar, if you read Macquarie's book, he refers to Chandrasekhar's paper because Chandrasekhar also uses, he has papers in 40s. After this course, and especially after Chris Jarzinski's advanced course, you should be able to go and understand papers written by Chandrasekhar 50 years ago. But even after this course, you might be able to understand them. So this is our decorrelation function. This is very generic. If this is equal to 1, you have an ideal system. But in general, this is complex, right? It is a function of 2 vectors. So it is a function of 6 variables, right? 3 components of R1, 3 components of R2. Going forward in this class, I'm going to make an assumption. We will talk still about interacting fluid, but we will talk about isotropic, spherically symmetric molecules. Clearly, water is not one of these. Yet what we do is kind of applicable even to water. You know, even though we make this assumption, it still sort of works, right? Things like argon would be perfect, but it's almost a rare gas. But there are many, many things, you know, like if you really zoom in, it's not going to, even ammonia is not spherically symmetric, but right, it's a question of how fast is that motion? Can you, in physics especially, we approximate everything as a spherical cow, right? So we are going to assume this. If we assume this, then going forward, we can say that G2 of R1, R2, which depended on 6 vectors, 6 numbers, R1x, R1y, R1z, R2x, R2y, R2z, will now depend only on one number, which is G2 of the distance between R1 and R2, right? Mathematically, what is this? This is square root of R1x minus R2x whole square plus R1y minus R2y whole square plus R1z minus R2z whole square. Okay, so it just depends on one number. And normally we call this number as R, right? It's just the radial distance. So going forward, what I'm going to do is to not talk about G2 of R1, R2 vectors. I will just talk about G of R. I'm not going to talk about G1. I'm not going to talk about G3. So why dangle this 1 and 2? When I say G2 of R, when I say G of R, it is implied that I'm talking about G2 of distance between R1 and R2, okay? And this G of R has a name. This is called the radial distribution function. So all the things that we introduced so far was really a preamble to get to the radial distribution function. Often people abbreviate it as RDF. Okay. I'm going to stop here for just a moment. Should I give an extension on this homework? Who thinks I should not give an extension? How many thinks? Should I? But then your weekend will be ruined. I don't want to be working on the weekend. Is that okay though?
Give us an extension, we'll procrastinate, so we'll leave it to the last minute again.
So my insight is I have a physics exam on Monday, which means that I would prefer to cram for the physics exam on the weekend, but also I prefer to cram for the physics exam today and tomorrow. So I'm like, maybe I turn it in now and then on the weekend I study for physics. Maybe I turn it, maybe it's due on Tuesday and I do it after.
Okay, I'm not changing it.
I'm just saying.
Not changing it. Yeah, I know my student Ricky is also taking that exam. This is Tom Mannion's class. Which class is it? Huh? Okay, but this is the, what course is this? Sixth, yeah. Last year Tom was teaching it, I think. Anyway, so we will get back to this question of extension or not, maybe later. So G of R is, again, just to remind you, this is G2 of R1 minus R2, and this thing is known as the radial. Why did we call it radial? Because it's looking at only the radius. We're looking at spherical symmetric system, radial distribution functions. And this thing is a big deal in describing, well, chemistry of anything, proteins, RNA, water, anything you want. G of R is really, really critical. So we are going to spend some time trying to understand what G of R is. In order to do that, I'm going to make a claim. I will make this claim and then I will prove it. And to prove this claim, I'm going to use Bayes' theorem today. Okay. So the claim is, while G of R sounds sort of abstract, right? If I asked you to define G of R, you will be like, well, let's start with P, blah, 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 blah. You'll be lost, right? It's hard to say what G of R is. Turns out, if you multiply G of R with rho, the density, that has a profound, not profound, it has a simple physical significance. Rho G of R, before I write it down, let me try to describe it by waving my hands. Let's say you are all fluid particles moving in this room, okay? And you are indistinguishable. So I'm not going to distinguish between Trevor and Max and Didi, okay? You're all the same. All I know is that there is one particle at the origin, okay? Another way of thinking about it is that in this box, even though I say all of you are indistinguishable, let's say I tag one of you, okay? I isotopically, I do something. So I tag one of you and I call this at my origin. So it's moving frame of reference or whatever, right? So you can think of it in two ways. Either you just assume that there is one particle always over there, or that you have tagged one of them, okay? Given this, now I'm asking you, given that there is one particle at the origin, what is the probability of finding another particle at a distance r from that? Okay, so I have my coordinate system, and let's say I have one particle over here, and I go out a distance r from it. So this is x, y, z. If I go out a distance r from it, it will be sort of a sphere, right? So I'm asking you, given that there is something at the origin, what is the probability of finding something at a distance r from this? I'm not saying what theta and phi because it's radially symmetric. Turns out rho G of R is this conditional probability. Rho G of R is the conditional probability of finding a particle at distance r given, and when I say distance r, I mean distance r from the origin, distance r from origin, given another particle is at the origin, okay? And we will prove this in a bit. but I want to show you why this is intuitive and why this allows us to calculate G of R from scattering experiments and things like that. So let's try to plot this for different systems. Let's try to develop. You can plot this. Given this information, now pay attention, and the next part is not going to be very mathematical, it's going to be intuitive. Let's draw an axis where the y-axis is G of R and the x-axis is distance R. If all of you were an ideal gas and there was no interaction between any of you, and let's say I managed to tag along one of the ideal gas particles. Now I'm asking you, what is the probability of finding another particle at a distance R from this one? For an ideal gas, will this probability depend on R? Didi is nodding his head. Yes, Trevor is nodding your head. No, can you guys fight and come to a conclusion? Didi, tell Trevor why. He should change his mind. He got scared of you. Good. So why is he right?
If it's an ideal gas, wouldn't they all be spread out to the equals?
Yeah, you don't care that there's something at the origin. You're ideal. You're like, I don't care. They will be spread out completely equal. So G of R for an ideal gas is going to be a flat line. And it should be equal to 1. Because if you multiply rho with that, so for an ideal gas, G of R should be equal to 1, because when you multiply it with rho, the conditional probability of finding a particle at a distance R is simply the density. If the density goes to 0, the conditional probability of finding something decreases, right? And if you want to be mathematically super careful, we are thinking about, you're ignoring a probability density here, right? So if you have an ideal gas and you found one particle over here, and now I'm asking you, tell me the probability of finding another particle anywhere else. Since it's an ideal gas, you can conclude this probability, this condition probability will not depend on how far out I am looking, because it's ideal. That's the first thing. So it's going to be a constant. Number 2, if this ideal gas is dense, you would expect this probability to double. If it's only 2 of us in this, versus if it's 4 of us in this, the probability should double while going from 2 to 4. Does that make sense to everyone? Julia, what do you think?
Can you repeat that last part? I'm sorry.
Okay. So first part is that we are all ideal. We are not talking to each other. If it's all ideal, then the probability that if I'm sitting here, one of you is sitting over here or sitting over there or sitting over there just does not matter, right? You're just moving around. So now let's say there is 10 of you. Now, condition number 1, you have 10 people in the room. So the probability of finding someone sitting at a distance R from me is, let's say, 5%. And this 5% is constant for the room. Now, let's say it goes viral that this class is really, really cool. And everyone wants to attend this class. And suddenly there are 10,000 people in this classroom. The probability will become much higher. That's what I'm saying, right? And in fact, it will become higher proportional to the density. Only for an ideal gas. For anything else, we cannot say that. For an ideal gas, it will become higher proportional to the density. And that probability is not G of R, that probability is rho G of R. So you expect rho G of R to increase linearly with density. So G of R is equal to 1, right? That's the idea. For an ideal gas, G of R is equal to 1. Better? Okay. You will again get confused, and that's okay. You know, that's how science is. You get confused. Science is a state of perennial confusion and getting rid of it and getting confused again. And if you enjoy that, then you should stay in science. If you don't enjoy that, get your PhD, do something else. I really enjoyed. So that's for an ideal gas. Now let's talk about a crystal. What happens in a crystal? In a crystal, you have atoms arranged in a very periodic manner, right? This, for example, is a simple cubic crystal. You have atoms only on the corners of the cube. For a simple cubic crystal, let's say this is my origin. And if I know that there is one particle at the origin, what is the probability of finding another particle, say over here? Slightly away from that origin. At a slight distance away from that origin. What is that probability? Ami, what do you think? It's a crystal.
So it's symmetric.
But I'm not asking you to go to the next corner. I'm not asking what is the probability of finding a particle here. I'm saying what is the probability of finding a particle, let's say halfway between. What is that probability? For a crystal? Is zero. It cannot be there. It's crystal. It's not just symmetric, it's periodic. You know, if there is a particle like this set of photos, all of you over here. If there is a photo here, the next photo is over here. I cannot have a photo somewhere right in the middle, right? That probability is going to be zero. So if I plot this for a crystal, this thing is going to be zero for a certain while until you get to the first nearest neighbor. And then it just picks up. So you're going to have a peak, which will look something like this at the first nearest neighbor. And then it will again go down. So this peak corresponds to first nearest neighbor. So in this case, this is the first nearest neighbor, right along the edge. In a simple cubic lattice, where is the second nearest neighbor? That's along this diagonal, right? Let me use the color blue over here. Where is the third nearest neighbor? That's along the body diagonal, right? So you will have peaks which corresponds to nearest neighbor. And so the second one will give you some peak, which looks like this. Then the third one will give you a peak that maybe looks like this, and so on and so forth. Okay. It's the same curve. I just drew different colors to make it clear what is it coming from. So this is third nearest neighbor. This is second nearest neighbor. Okay. Yeah.
So why are they different heights?
We are going to talk about it in just a moment. If it was a perfect crystal and atoms were sitting exactly at the corner, these things would be delta functions. But it's not a perfect crystal for the simple reason that there is thermal fluctuation. Another reason there could be defects. So these peaks will have some width, right? So this width, which is, you can calculate it as full width at half maxima or something like that. Width corresponds to imperfections of different sorts. Imperfections could simply be movement due to thermal thing or some sort of defects. Why are the heights different? Any idea? It's a very good question. Go ahead.
Different numbers of atoms at each of those distances.
Yeah, so the heights, and that's what is super beautiful about this. The heights tell you the symmetry of the crystal. And you can calculate the precise height. Face-centered cubic will have exactly same ratio of heights. Body-centered cubic will have a completely different set of heights. So the point here is that the density of how many neighbors do you have change from packing to packing. So, and if you have never done solid state physics or solid state chemistry, that might sound strange. You know, let's talk about 2D crystals for the time being, right? So 2D crystals, you have simple cubic that looks something like this, right? So G of R, the height in G of R, what is G of R? Rho G of R is the conditional probability, right? So G of R really corresponds to how many neighbors do you have, right? So in a simple cubic, and I'm doing 2D just for the sake of giving you all intuition, okay? And this is stuff which is not there in Chandler, probably not in any book, so bear with me. I hope it will be useful. So in 2D, the number of first nearest neighbor is equal to 4, right? How many second nearest neighbor does this thing have? Let's count. This one, this one, this one, this one, right? That's also 4. What does it tell me about rho G of R for a 2D crystal? The peaks should have the same height for the first and the second. right? For the third, I will have to draw more things, and you can go and count, you get the idea, right? So if I had, so this case, if I was plotting G of R, it would look something like peak over here and exactly same height peak over here, right? Because the coordination numbers are the same. And that dot dot, it will look like that. This is not the most perfect packing in 2D. The most perfect packing is a hexagonal crystal. In fact, even in 3D, the most perfect packing, and you can see it when you stack oranges at a shop. The oranges are always packed in a hexagonal packing. That's why they maximize the coverage of the box. Does anyone remember what is the packing efficiency you can achieve with face-centered cubic packing in 3D? 82%.
Oh,
Yeah, good job. It's 82%, and this is known as Kepler's conjecture. Kepler, who was the guy, in 1600s, hanging out with Copernicus and all those people and making bold claims like Earth is moving around the sun and things like that. Kepler made this as a conjecture that this is the maximum packing you can achieve. In 1600s, it was proven in 1990 or 1995 by using a proof that really involved computing. There is no fully analytical proof of this. That this is the most perfect packing was proved. People broke it in like many cases, and it took 400 years to prove Kepler's conjecture. As you go to higher dimensions, this thing changes. In 8 dimensions, things get funky. And I had not a friend, there was someone from India who was very famous. He had like this all India rank 1 in the IT entrance exam, then he went to MIT and things like that. His PhD thesis at MIT was about how to pack spheres in 8 dimensions. And turns out in 8 dimensions, there is some dip that happens in the maximum packing efficiency you can achieve. And people use it to come up with anti-spam software, believe it or not. So this guy then became a mathematician at MIT. At MIT, mathematicians don't get tenure. So he did not get tenure. Don't feel sorry for him. Then he started working at the most successful hedge fund, which is out there, called Renaissance. And there is a book called The Man Who Won Wall Street, about Jim Simons. That's the guy who runs it. So Jim Simons' modus operandi was to get people who don't get tenure at MIT and hire them at Renaissance. I'm pretty sure he's making around $4 million a year right now. So, huh?
He just died.
Who? Simons died, but not my friend Abhinav Kumar. He's still alive.
I didn't.
Yeah, he's still alive. Simons died. Yeah. So anyway, but let's come back. I find it's interesting, like packing and things like that. And it matters a lot, for a lot of chemistry, that this is the highest packing you can achieve. But we are in 2D. Let's go back to 2D. In 2D, what is the number of first nearest neighbors you have? That's 6, right? So you already expect that this peak will be sort of higher relative to what you had for that one, right? It should be higher because you have 6 neighbors. But now the harder question, I don't know how to calculate it. Can anyone help me? I will have to pack more spheres. All right, let's go for it. Let's try to do this. Next time you are sitting in a boring seminar, you can start doing it. Sometimes Chris Jarzinski does that. He will be sitting in a seminar, nodding his head, and I look at his notepad and I see he's doing something completely different. Did I get it correct? You get the point, right? But you can go and count now. How many nearest neighbors do I have? I have 1, 2, 3. Well, it's a bunch of them, right? So I don't know how many it is, but hopefully Julia will agree with me that it's many more than the number of first nearest neighbors, right? So what does this mean for this curve? It's going to be much higher. Twice as high. I think it's double, but you can check, okay? And dot, dot, dot. So G of R, if you could measure it, tells you something about the underlying symmetry. It's really powerful, right? And by measuring this width, it tells you something about the defects in the crystal. So when I was an undergrad, my first paper as an undergrad, my first 2 papers, the second one is kind of a funny story, was to use Monte Carlo simulations to calculate G of R. And I did it for a bunch of crystals. I was very proud. Wow, I used these fancy Monte Carlo simulations. And one day I realized that for half of them, all I needed to do was to solve a quadratic equation. So I told my advisor, like, he was like, well, let's write another paper. So I wrote another paper, which is 1 page long, saying, well, half of it we could have done with just solving a quadratic equation. The other half is good too. But what I did in that paper was not G of R. It was something related to G of R, and that is known as S of K, or the structure factor. R lives in real space, right? K is the Fourier space. It's the inverse space. It's the reciprocal space corresponding to R. So G of R, if you take a Fourier transform, you get S of K. And if you take an inverse Fourier transform of S of K, you get G of R. And S of K is what you measure in scattering, be it XRD, be it neutron scattering, be it whatever you have when people go to fancy, complicated labs like Argonne National Lab or whatever. It could be even synchrotron or whatever you have. S of K is at the heart of a lot of things. People go and measure this S of K all the time. And now you see why it's so powerful, right? If you get S of K, all you need to do is to apply an inverse Fourier transform, and there are lots of software which can do that. You get G of R. Now you can look at the peaks in your G of R. You will be go, oh, this material is body-centered cubic. Oh, this material is something else. Oh, this material has a symmetry that no one knows. You can look at the width of separate thing. Maybe you will see that the first nearest neighbor shell is very tight, and the second nearest. So if this one is very tight and this one has a lot of width, you will be like, oh, there's some funky defects going on in the second nearest shell. I need to investigate this, right? So it suddenly opens up a lot of things. And that's why this G of R, I took so much time to get to this. That's why it's so powerful. And hopefully you can see why it's so nice. So, and I will show you later that if you assume that your U, the n-body potential function is two-body, then G of R contains all thermodynamic information. You want to calculate enthalpy, you can calculate it from G of R. You want to calculate heat capacity, you can calculate it from G of R. It's like awesome, right? It's almost like, so far our favorite function was hopefully the partition function. Once you have it, you know everything. Now you should be like, move away partition function. All I want is G of R, right? And now I forget, for a two-body potential term, no, actually, for construction, G of R will be useful only for two-body interactions, right? Because G of R, remember, we assume spherically symmetric type of interactions, right? So you can calculate G of R for anything else. It won't contain all thermodynamics because there is much more going on. But if it's a spheric, to a first approximation, you can already get a lot of stuff. So, and we will show how to do that. But suddenly it opens up something. And many of you will be, I'm ready to bet like 30–40% of you will be dealing with G of, no, actually 80% of you will be dealing with G of R at some point in your scientific careers at University of Maryland, either by doing experiments or by doing something else. If you do scattering, you will deal with it all the time. If you're doing computer simulations, you will deal with it all the time. In fact, what people do, and there is sort of a symmetry between computer simulations and experiments. In computer simulations, what we have is the n-body potential, right? Given this n-body potential, we can do molecular dynamics, we can do Monte Carlo. What computer simulations do is to actually simulate things atom by atom, right? So Disha, for example, is an undergrad in my group. She looks at RNA, right? She puts a bunch of RNA molecules in water, and she studies how is the RNA moving around. What she knows is the force field governing the RNA, right? Depending on which conference she goes to, people will either agree with that force field or not agree with that force field, right? Because its RNAs are very complicated, things like that. So what Disha does effectively is to take this U of Rn, simulate the atoms moving around, and then calculate G of R. In experiments, it's other way around. In experiments, you get S of K from your scattering, which you Fourier transform in your Fourier transform to get G of R, and then you try to come up with predictions of what is the interaction that is going on, right? So there is sort of an asymmetry. And this is also why you see there is experiments and computer simulations go hand in hand, right? You can do those things together and try to get a sense of what's going on. So you did some experiment on some funky new material or chemical, you interpret something about the U of R. Now you go set up a computer simulation, you study it, you see whether there is consistency or not. On the basis of computer simulation, you make some predictions. Well, if I go and change my carbon to sulfur, this should happen, and you go and make that thing, right? So you can have back and forth. So it becomes very nice. Any questions about this? So for two body interactions, if a system had only two body interactions, G of R contains all thermodynamic information, which is kind of awesome. And we will get to this later. So in the remaining 20 minutes or so, what I'm going to do is to give you intuition. All of this was on the basis of my claim that rho G of R is indeed the conditional probability. We haven't proven this claim yet, right? Chandler helps you in proving this claim. A lot of people hate Chandler's book. There are two reasons for that. Number one, Chandler was sort of obnoxious. So when I was a postdoc in Switzerland, he visited my advisor, Michele Pardinello, and I had just had lunch, and he comes up to me, and he had a very nasal voice, and he goes, "So you are the guy trying to get dynamics from metadynamics?" I was like, "Yes." And then he grilled me for 2 hours. My first interaction was with Chandler was a 2-hour intense discussion. And he would go to conferences and give everyone a hard time. That's one reason why people hated him. The other reason people hated him, or at least his book, is because it's a bit terse. It does not really tell you things. So like for this one, it just tells you, like, justify this formula or prove this claim. It doesn't say much. So we are going to actually prove this. So any questions about this before we get to the proof? Okay, let's draw it on the next page. I'm still thinking about the homework. Yeah, fine. Give it on Tuesday. It's okay. I'm feeling good.
Thank you.
Homework 2 is now except Max. Tuesday in class, and I will soon announce about the midterm also. I will do it around when I have to miss one class when I go to Princeton on 22nd or so. So it'll be around then, and you will have time to do. Second midterm is a lot of fun. It's the part that people enjoy. So don't stress over it. Okay. Second midterm, you will have to try hard to not get 100. And I will tell you one of those things. For example, you will have to draw a figure. And even though I complain all the time, a figure should look like a figure, yet a lot of you will make a figure which will be a box with a bunch of text inside it. So I will cut your points. So it's very clear. It's easy to score 100. Follow the instructions and enjoy the process. Okay, you will learn from that midterm. Final, I have no promises. So I'm not going to change the homework due deadline on the website or the Slack and things, so just, yeah. Okay, so what are we going to do now? We will prove our claim that rho G of R is the conditional probability of finding an atom at a distance R, given one is at origin. Let's use the language of conditional probabilities. R given 0, right? This is how conditional probabilities are written. P of A given B is probability of event A happening given event B has happened, right? That is the conditional probability. Furthermore, P of A given B is P of A intersection B divided by P of B. Okay, this is Bayes' formula. So we are going to use this later. So let's get started. In order to do this, I'm going to draw a box. In this box, let's call this axis X, axis Y, axis Z, even though I'm not really going to use the dimensionality, the components, but still. And now let's say this is my origin and I have some particle at the origin. And I'm trying to ask, what is the probability of finding something, a distance r, right? Even though I'm drawing one direction, strictly speaking, it is on the surface of the sphere centered around the origin, okay? So I want to calculate this probability. Well, I will start with the left side. I will try to look at rho g of r. And now you will have to brush up all your formulas that we defined for P2 and ρ2 and things like that. So let me walk you through those formula one again, because we are going to use all of them. Recall that P1 of R is this probability. P2 of R is integrating the Boltzmann factor over all R3 to Rn, right? So this was P1 and P2. This was the probability of today. My models were Atley and Rachel, right? So this was assuming the identity, not distinguishing, actually distinguishing them. Then we got, those were distribution function. Then we got to reduced distribution function where we defined ρ1 and ρ2, right? ρ1 was n multiplied by P1, ρ2 was n multiplied by n minus 1 multiplied by P2, right? And now I'm not caring about which particles, any two particles will do out of an n particle system. For a uniform isotropic fluid, even with interactions, let me emphasize this, even with interactions, as long as it is uniform isotropic, ρ1 of R1 is the density, n by V. For a uniform isotropic fluid with no interactions, ρ2 of R1 R2 is equal to rho square, right? And that's when we introduce G2 of R1 R2, which is the difference between ρ2 of R1 R2 and rho square, right? Then we looked at symmetric systems, spherically symmetric. So instead of G2 R1 R2, we looked at just G2 of R1 minus R2, and we called that G of R. Okay, this is the recap. And I know this is a lot of stuff. It's simple, but it's many new symbols all of a sudden, right? So that's why it's natural if you get confused by these things. So with that, now let's come back to this. So rho g of r, I'm just going to do a bit of algebra. I will multiply, divide by rho. This is the same as 1 by ρ2 g of r, right? It's nothing profound. Now it's like, this is like we are living backwards in time, okay? Everything is gonna go backwards. We will introduce symbols. What is that movie from the director of Inception? Huh? Tenet. It's like Tenet, okay? Everything is going backwards in time. So now I realize, well, how did I get to G of R? My G of R was really G2 of R comma 0. Remember? That's why I said it's like Tenet. We are going backwards. Huh? Technically, you cannot. Yeah. I'm using some creative license here. Benjamin Button, how about that? There it does go backward. Or Picture of Dorian Gray by Oscar Wilde. There are many examples. So ρ2 G2 R0. Again, we go one step backwards. What is ρ2 G2 R0? ρ2 G2 R0 is 1 over ρ2 with bracket. Sorry, R0. Right? This is how I define G2 of R0. G2 of R0 was the ratio of ρ2 R0 divided by square of the density. So now I have 1 by ρ2 of R0. Okay, almost there. And I want to emphasize here, this is only for uniform isotropic fluid. It has interactions. If there was no interaction, then G of R would be 1. It would be ideal, right? So, but it is a uniform isotropic fluid. So what we have so far is rho G of R is equal to ρ2 of R0 divided by rho. Again, one step backwards. What is rho for a uniform isotropic fluid? Claim number 1. Rho is ρ1 of R. Right? But it's a uniform isotropic fluid. So does it matter that I write ρ1 of R or ρ1 of 0? It's the same. It's uniform. So this is the same as ρ2 of R comma 0 by ρ1 of 0. Right? Everyone still with me? But Tenet has blown your head. It's literally going backwards, you know, it's like everything we are introducing more complicated symbols in every step. Now, we go from rho 2 to P2. And remember, rho 2 was n multiplied by n minus 1 multiplied by P2. Rho 1 was n multiplied by P1. I am going to ignore the n's and I will just say that therefore rho g of r is proportional to P2 of r comma 0 divided by P1 of r. Why? Because the proportionality constant is n multiplied by n minus 1 divided by n, right? So I'm getting rid of the proportionality constant. Oh, and I'm not using r. I switched from r to 0 at this point. Notice this is just the base formula. P2 of r comma 0 is the joint probability of finding one particle at r and one particle at 0. P1 of 0 is the probability of finding one particle at 0. So this is nothing but the conditional probability of finding something at r when there's something at 0. So we have just proven, and you can see why I was careful with the probability, because there is a proportionality constant that is missing. You have to be careful about n if you want to normalize it to 1 and things like that. So rho g of r is indeed the conditional probability of finding a particle at r given something else is at 0. And I'll stop here. I will stop. This is what I wanted to cover today, but I'm going to stay here for a couple of minutes. And if there are any questions, you guys can ask me. Yeah.
Wait, so is the initial plane supposed to be proportional instead of equals?
It should be proportional, strictly speaking. Yeah. Even Chandler is sloppy about it. Chandler calls it equals. No, it's proportional if you want to be very careful. We ignore the probability density. We are very, very careful. We are sloppy with n and things like that. Yeah. If you write it is equal, I won't deduct any points. It's okay. The point, the method is, the message is given. So rho g of r is the conditional probability, and that explains why rho g of r is so powerful. If it's a conditional probability. What is scattering? Scattering is the same idea, right? You bounce things and you see what is the probability of finding something elsewhere, right? And that tells you what is the probability that if something is here, what is something else here, right? That's what scattering measures. That's why these things are so connected. I want to stop here, but I want to tell you next time what will we start with. I'm not going to write anything down, but next time what we will do the following exercise. Let's say you are all, next time's exercise will not involve just 2 of you, but all of you. Let's say you are an isotropic fluid where everyone is interacting with each other through some complicated potential, which is n body, right? But it is still an isotropic fluid. And I now focus on 2 of you. At this point, I'm going to pick 2 of you. I will pick, who should I pick? Didi and Noah, okay? No, I should go back. I should pick Disha today. Disha and Fatme. I pick Disha and Fatme, okay? And everyone else is doing what they are doing. The question I'm asking now is, what is the force between Disha and Fatme? If it's an ideal gas, there is no force, right? They are not interacting. If they were in isolation and all of you were not there, then maybe I could calculate this thing by simulating. I would model Disha and Fatme, and I would just separate them by certain things and look at the potential energy, right? And make some sort of a curve. But now this question I'm asking is much more complicated. I'm asking, what is the force between Disha and Fatme averaging over everything else? And this is different from the force between Disha and Fatme if you were all not there. I mean, it makes sense, right? If no one is there, then the force between Disha and Fatme would be independent of where they are. Now it will depend on what you guys are doing. If you guys are all hanging in this corner, maybe the force between them is very different. They can move around, do whatever. But if they come and sit in where you are located, then the force is very different. What we are going to show that to calculate this force, which has a very particular name, this force is called the potential of mean force, or the energy derived from this, the energy relate, force always comes from differentiating the potential, right? So we are going to talk about the concept called potential of mean force, and we will show once again, this force between two particles averaging over everything else comes from taking the log of g of r and differentiating it. So g of r contains this information. That's also why it's again powerful. If you're interested in this, I do recommend, I mean, now you won't read it. Now you have homework, an exam. Max is totally not going to read it. But if you have time, read through Chandler's chapter. This is complex stuff. It takes time to appreciate it. Okay. Otherwise, I will see you on Tuesday with your homeworks. Thank you.